So this afternoon, I know it's quite late, but we're going to be walking through these few equations. By the time we finish, we should know a bit more about functional programming. If you're wondering what the domain is, it's actually a statement of compositional evaluation semantics for contracts. That is, how do we assign contracts for engineering jobs? And it's by a guy called Simon Peyton Jones, an adventure in financial engineering, and this really is an adventure. Fortunately, we're not going to look at this paper. But it's 16:20 on Friday afternoon, and I prepped to have this session quite late. And so, to keep you guys awake, because I'll be doing a lot of typing and mumbling into the microphone, I've decided, together with my boss Ryan, to give away this afternoon one of what I think is the finest bubbly in Cape Town, which is from Morgenhof Estate. It's a Brute Reserve 2006. It's not SodaStream. It's Method Cap Classic. And the way you're going to get one is that if you pay attention and you have to answer this question. And the most interesting answer, Ryan, you'll be the judge of the most interesting answer. We'll take 5 answers, and you pick the best one. And the question is, what is the difference between data and function? Right? So that's the question. You can't answer now, you can answer at the end. Right, so let's get rid of Simon Peyton Jones. So I'm Aslam Khan. My boss Ryan forced me to write Haskell sometimes. You'll find me at Aslam Khan without the A in the surname. I'm not related to Dinesh in any way whatsoever. He supports Pakistan. Where is he? Dinesh, you around? Oh, sorry about the 43 all out, man. Really, sorry. You know, it's okay. Oh, man, we're almost there, man. We're almost there. We're almost there. I knew it was going to come up. Chokers. So we're gonna walk through some functional programming, right? And the reason why I chose this topic is because, not to satisfy my own little curiosities around it, is that we actually use a functional language that's pretty reasonably functional language for a lot of the time, and that's JavaScript. Okay, and a lot of us are writing this JavaScript stuff, and we're starting to do a lot more with JavaScript, especially client-side, and also with the Node stuff, Backbone and Knockout and all of those nice things. So some of us are even actually building domain models, etc., in JavaScript. And one of the things around functional programming is that it's always been, like the set of equations I've put up, it's always been completely unapproachable to me. It's something that I just couldn't get into, because every time you pick up a paper, the first 3 pages are really nice English, and then someone goes into category theory, and they all point to the same page on Wikipedia, and it just doesn't work out for me. Okay, so what I'm going to do is that I'm actually going to show no Ruby today. I've chosen languages that don't have superfluous do-end block syntax. So everything I've chosen is just so that I type less. Right, so here we go. On this side, the light side is where I'm typing. On that side is output, if there will be any. So the first thing I want to do is just pick up on a couple of small functions. Let's just say I have a function. Oh, by the way, I'm typing in CoffeeScript here. Okay, so I'll explain the syntax once, and then the rest of the time you'll pick it up. There's nothing else about it. So I want to create a function that calculates postage and packaging, and it takes a number from an invoice or whatever, and it just adds 30 onto it. Okay, that's it. So what this means in CoffeeScript is that P is a function that takes one argument in, and this is the body of the function. Right? Adds 30. So the jQuery gods will forgive me, but I wrote a tiny little shorthand thing to output to the console, and I'll just say what's P of 100, and you should see 130 on that side. So nothing spectacular yet. Well, it was spectacular when the first time I got this thing working on the side. Now let's just say I had another function, right? And this one is to calculate discounts, and the way I do that is that I say it's n times 0.8, we're a generous crowd, we give you 20% discount. Okay, I'm not outputting the result of that to you, right? Now, let's just say we also had tax, right? And what we do with tax is that it's n times, let's be some dictatorship, 1.5. Okay, so it's 50% taxes. Now, what if I want to calculate, I want to apply postage charges after discount. So I'll say postage after discount equals some number n, and it's nothing spectacular, so it's postage after discount of n, right? And if I want to calculate tax on that, right, tax after postage and discount, it's going to be of some number, whoops, and, oh, sorry, the typing is bad because I'm using Sublime. 2. Okay, without VI key bindings. So what we're going to do is we're going to apply the tax onto that, like that, okay? Now, I'm just going to line this up a little bit here, right? And I want you to take a note of that form, right? That. They look exactly the same in structure, okay? So take a function, apply it to the output of evaluating a function with n passed into it. So I'm just composing functions. That's all I'm doing. Evaluate something and pass it to another function. And we do that all the time. So what's so spectacular about this is that, well, the spectacular to me, is that I could actually express that notion of function composition as a function itself. So I can say, I'd like a function called compose, which takes two functions, and it's going to return to me another function where I can apply f of g of n. Now, if you look at this form here, that form is exactly the same as that form. You all with me so far? Okay, good. All right? So I can then replace what PD is about by just saying, hey, you are composed of P and D, and you are composed of T and PD, right? And in case you don't believe me, right, PD of 100 will be 100, take 80% of 100, which is 80, plus 30, it should be 130, right, 110, and that's what I get. And if I take the next one, TPD of 100, I'll get 165. So first thing, right, I can compose functions. That's the first thing about functional programming. I can take two functions and coerce them to work together and treat the output of that as a separate function. That's very different from just, linguistically, it's very different from saying, oh, wrap this function inside another function, wrap this method inside another method. It's different from that. Now, let's just say, for argument's sake, that as time goes by, we get some really crazy calculations, right? And we actually want to start tracking what the output of those calculations are. So for example, if I'm applying a discount to 100, I want to say I take 100, I pass it into discount, and I get 80. I just want to trace that. Now, if I'm being quite gung-ho about it and it's the day before the sprint review, then I would go P equals something n, right? And I will go and say, same thing, n plus 30, but I'm just going to stick some debug information in, and that's going to be plus postage. And I could do the same thing with the discount. Whoops. And that's n times 0.8. And here I want to know that it is minus the discount, that. Okay. And if I just keep those out of the way and I now run it, whoops, didn't work. Not a number, right? it's broken. That implementation will not work. And it doesn't work for a very, very simple reason. Okay? What our original functions were doing was this, right? It was some function, right, that took something of type A and returned something of type A. So take an integer, take a number, give back a number, right? And what we actually did to those functions P and D is that we did this. Take a really nice clean number and give back this and some string. Now it's no longer composable because the output of the function does not match the input of the other function. So I cannot coerce them. I cannot put them together. I can't glue them together. What we actually want to do in order to glue them together is say this. Right? Write a function that takes an array, a number in a string, and returns a number in a string. Now, I can go around and start hacking this, right? And remember, we're getting to sprint review time and last commit and merge hell and shit like that. So I actually want to come up with a way to keep these functions absolutely pure, as Ryan was talking about, is that I actually don't want to fiddle the structure and signature of those things. Those are functions that I can test very cleanly by themselves. They've got nothing else to do with superfluous things which I just want as output information. So what I want to do is that I want to come up with a way of coercing those two functions to produce the same output with this trace without touching the structure of those two functions at all. The whole idea is don't touch those original pure functions. And I'm going to use some very weird words here, but I'll use it here just so that when you start getting the energy and inspiration to read that stuff on Wikipedia, you'll see this word as well. So what we want to do is that we want to take bind as a function that takes a function, right, like P or D, and S, which is like the text that we want to see, which is, okay, pos for postage and discount and dis for discount. And what it does is that it returns a function that takes R. Now R, the structure of R is exactly like this. Okay, so it's a number, right, followed by a string, followed by a number, followed by a string, and we carry on. So what I'm really after here is actually what's the number. And it's the first element. And what I want to do is calculate the value or apply the function to that first element. So it's f of n. And I want to build up the output array again. Right, so now it's v, right, and that nice string that we had of, whoops, and then what we had before, okay? So now what we have is we've actually written this function. So I can create a new function, leaving p alone. Let's call it underscore p equals a binding, right, of P and whatever I wanted to call it, which was plus postage. Okay? Remember getting this bottle afterwards, eh? No, you don't get the answer, forget it. Ryan and I will drink it, we're fine. So if I had to now output this, okay, what is P of underscore P of 100? Okay. Where am I going? Let's get rid of that. Okay. So I'm getting this weird thing here, which is not a number again. Okay. And that's because we need to give it an array, because we said it must take in an array, right? And that array must do something like that, which is just an, whoops, like that. Okay, and now I get it. So if I look at this output here, this last output at the bottom here, what I'm saying is that we took a number 100, we've passed it into the postage function, and we've got 130 back. Okay. Now it's really annoying that every single time I'm going to have to do that. Okay. Because when you can imagine that when I start writing the underscore D trace function, right, it's bind of D and minus discount. And now every single time I want to use that, I have to do this. 100 that. Okay? Now that's really annoying that I actually have to do this here all the time. Okay. So why don't we write a function that actually does some of that for us? And I'm going to call that function unit. Right? And what unit does, it takes a number x, and all it does, it gives us x with some default string. Right? And now I can say do that to 100, and it now works. Now, if I look at this, right, this bit, it's take a function, apply it to another function that took a value. That sounds familiar. It was composition all over again. Okay? So I can actually simplify this and say, hey, let's create a function which we call lift, right? And it just takes a function and it composes it with unit, right? So now what I can do here is say a new function double underscore p equals lift of underscore p. Then I can actually then just say output, and I'll get the same output. So what this tells me is that by leaving that original pure function all alone, I can start coercing that function into something that looks totally different, that actually catches and adorns it with additional information without having to go and muck around deep down into the original function. I can keep my domain particularly pure, and all this other plumbing and craft that comes along, I'm just going to coerce those functions to look like other things and to start using them quite liberally, right? And these bind, unit, and lift functions are independently testable anyway, right? So if we went a little bit further, right, I could just simplify this. I could say lift bind. Okay. Right. And I could do the same thing here, which was lift and bind. But for now, I want to go down to that other calculation that we had here. This one, okay? If I look at this one, now that I have lift, bind, and unit in place, I can actually just go and say lift the composition of P and D, right? And then if all else, if the functional gods are good to me, I could say 100, and there's a unnecessary thing there. Like that? Oh, you guys are lying. Bind, lift. Let's cut to the chase and just take the prepared one, which is basically that. I'm going to save us some time and just take that bit, put it in here, which is the same thing. Okay. Let's close that one off. Right. So here we get the output. So 100 is passed into discount. I get 80. I take 80, pass it into postage and packaging, and I get 110 by just using lift, bind, and compose. So what we've done is that keeping those functions pure, we can actually write functions that act on those functions and glue them together. In the object-oriented world, the way we do this is with that book called The Gang of Four Patterns, right? That book of polymorphism is all about how do we reshape things so that we can actually glue them together. That's what it's all about, okay? This thing here, philosophically, what we've done is that we've got something that had a number, and we want to adorn that with additional state, which was that trace information, right? So what we've actually done is that we've modeled the side effect of that function. We've introduced a deliberate side effect. And in the world of functional, that is known as the state monad, John. Right. So if you want to, this was the simplest way I could actually explain what the state monad is, which is how do we coerce two things to carry additional state when we still want to keep that original output the same and pure. Right, so far so good. Now, next language. Let's get rid of that. Go away. Right, Haskell. So I'm typing on the dark side. I'm in the Haskell repo, and I want to introduce this thing, which many of you most probably have done. I want a function that does age cutoff. It checks whether you're over a particular age or under a particular age. So it's, well, I have to say let. And if I then do age check of what's the cutoff is 18, and I give it 20, false, you're over age. And if I gave you 10, it's underage, right? But here's the magical thing in Haskell. Everything is what we call curried, right? And that is, it's partial evaluation of functions. So I can just say age check 18. I always get this wrong in the repo. Let. Now I can say under 18 of 10 is true, and under 18 of 20 is false. Now that looks so trivial, right? But basically what we've done is that under the hood, that value that we've passed in here has actually, it's now bound. It's effectively create a tiny little closure. It's bound inside the closure for you, and now we have this thing. So everything in Haskell is curried. If you want to do the same thing in something like CoffeeScript, you'll end up writing code that looks like that. Okay, without the dashes in the beginning. Right, so yesterday, Chris at Autonomous did Fibonacci sequence. I mean, no functional talk is complete without Fibonacci. So let's write that out. Let fibs, all right? Now, I want to explain some pretty weird syntax for you here, right? With Haskell. So let fibs equal to 0, the start of an array, with the next element of the array. So imagine a colon means added to the array, right? Push it on. And then after that, we're going to do this really weird thing here, right? Oops. Now we're going to say, well, the next thing after 0 and 1 is the output of a calculation which does zip width. So zip width means take two arrays and just zip them together, right? With plus, okay, of fibs, which is the structure itself, and tail of fibs, which is take the end of it, right? And now if I just type fibs, oh my God, it goes on forever. It'll never stop, okay? So what we've done is that we've actually defined an infinite data structure recursively. So how do I make it stop? I say take the first 10 of fibs, and I get that. And just to annoy Chris, what are you doing? 40. In 2-point-something seconds on the JVM. In fact, I wonder if I can get it to 2.7 seconds. Nah. Yeah, there we go. Okay, so, all right. So that's a quick introduction. There is some more stuff about Haskell which I don't want to talk about. If there's time, I could do it as a bonus thing. But the interesting thing here is that this idea of currying, which is partial application, not partial evaluation, which Constantine was talking about in the morning, yesterday, and the fact that we can describe in a very pure way what Fibonacci, what a structure really, really means. Okay. Now, the stuff that will actually answer the question well, give you the best answer for that, is the next thing. And I'm going to run through that very, very quickly. And that is, given just the idea of a lambda, can we create some crazy data structures from that? So let's see. Right, this is Python, okay? So the first structure, the first function I'm going to make, lambda xy here, means take create a function that takes x and y, returns a function that takes m and applies m to x and y. And who's familiar with Lisp here? Car, coulder, right? So car is a function, a lambda, that takes another lambda p, applies p to x, y, and just returns the first of the pair. And coulder returns the second of the pair. That's the other part of it, okay? So if I just type in on this side here, what's cons, it's a function. What's car, it's a function. What's coulder is a function, right? And if I just start creating a list with cons, which is construct, right? 1, comma, cons, 2, comma, cons, 3, comma, none, to just terminate it. Hey man, it's starting to look really lispy with all those parentheses. But if I said, okay, what's car of x? It's 1. It was the first one, right? It was the one side of it. And what's coulder of x? Right? It's a function, okay? Now, if I just shrink that like that so we can see it a bit better, I could say that head of a list is car and tail is coulder. And if I want to work with head of the tail of x, I'll get 2. And head of the tail of x, tail of x, I get 3, right? So this is just getting all listy about the world, right? So notice one thing that's happened here. Nowhere in this code did I actually assign a value to a variable. Everything is bound inside a closure, inside a lambda. If that's not a mind warp, I don't know what's going to get you going. So let's create a tree structure, y, right? And we know these tree structures take two things, a left part and a right part, and we'll just create a very shallow one. Okay? And what I'm going to do, I'm going to treat left as the car, left as the car operator and right as the coulder operator. And if I say what's left of y, what did I do? What did I do? Huh? Oh, did I? Thank you. Someone's paying attention. Okay, so let's just go pretty quickly here and take that. Ah, it doesn't even work. Y equals cons of 1 and 2 and cons of 3 and 4. Is that better? And if I go left of y, we start getting 1. And if I go what's right of left of y, I get 2. Now, again, it's really crazy that from 3 very primitive functions of, create this thing called cons, create this thing called car, create this thing called coulder, we can start creating pretty impressive data structures. Now, these are really trivial ones. And I'm going to just walk you through this little bit here, right? And I'm not going to explain it in detail, but basically, this entire function called reduce, right, or fold, is defined completely in terms of those early functions that we created on top. This one called range, which gives us 10, 9, 8, 7, 6, 5, 4, 3, 2, is defined completely in terms of itself and those functions, those primitive functions we created, which then means I can create a factorial by using reduce, range, car, and coulder, and sum as well. Now, if I have to, stop it. And if I have to say what's sum of 5, I should get 15, and sum of 100 up to 100 is 50, 50. And a factorial of 5 should be 120. Now this is really starting to get really, really weird that we can actually start treating data as functions. It's really, really crazy that we can do that. Now, where does that leave us? Very far from Simon Peyton-Jones' paper, okay? I want to summarize it for you like this. So firstly, having higher order functions, which we saw in CoffeeScript, Haskell, and in Python, right, gives us, it's a fundamental building block, right, of functional programming. Without that, you can't have a functional program. Function composition is an awesome thing because it allows us to actually combine things and coerce things into each other. Bind, unit, lift, also one more word called return, which is not return like you understand it in imperative languages. That's actually your visa to monad land. Okay, so if you're going to go further into monad land, get to understand what those things are. The one that I showed was a state monad, and there's lots of other monads like the list monad, etc., which actually allows you to, where bind and unit are defined differently. Right? Partial application and occurring gives us some brevity, and it allows us for some kind of reuse. Recursive functions create some really, or recursive data structures, or infinite data structures, come up with some very declarative way of describing certain things. Once you have that, right, you will absolutely wish that you had tail call optimization. Without tail call optimization, you will blow that JavaScript stack in your browser very, very, very quickly. So don't do it for real with JavaScript because it doesn't have tail call optimization, right? You'll just blow the stack quickly. I didn't go through data of functions, but when we started talking about the Lisp stuff, okay, whoops, here, data of functions. The whole idea of Lisp is that why everyone says that, oh, Lisp is just, every language is like Lisp, because when you have high order functions with about 4 or 5, I think this maximum in the original Lisp paper, there's about 6 primitives in addition to high order functions. With that, you can build basically the whole of Lisp. And from those things, you build up macros, and you go just further and further and further, and that's what you get out of it. Okay. So my takeaway with functional programming is that I think it's within reach. I think it has a place within the way we write Node applications. When we start going into indentation in Node, function composition, all of those things help. Or you can get one of those panorama screens. Okay. And hopefully you actually get a feel that you can actually start modeling some of the domain stuff. If you're using things like Backbone, etc., where you are modeling domains, you can actually start doing it in a very, very elegant way without polluting those pure models with all sorts of other adornments. All right. So that's me. That's come to an end. I'll take questions. Then we'll take answers. How's that? Okay. Any questions? Yeah. You missed the beginning. I said I've taken languages that made it in did not have superfluous block things. Yeah. So why did I ignore Ruby? Okay, because this type of stuff that we're talking about, you should not do with Ruby. It's as simple as that. There's a lot of stuff out there where people are trying to explain functional concepts with Ruby, and you will go through, you know, lambda hell, and the syntax doesn't allow for it, etc. But beyond that, it's a very, very good object-oriented language with a very decent meta-object protocol, right? The types of things that you're doing here, you most probably could get some kind of similar effect using metaprogramming. Here we're not using metaprogramming, we're using first-class primitives. I don't encourage people to try to get really functional in a very pure way with Ruby. You end up writing code that's not worth the effort. But when you're swapping over, and a lot of us are becoming very polyglot in the way we're developing systems, when you are using something like JavaScript, right, take advantage of what it has. Really make it sing and hum for you. That's what it is. So nothing against Ruby. Well, actually lots, but nothing really. Okay. Anything else? Right. So if there's only one person who's going to answer, what's the difference between, okay, okay, hold on. We're going to take 5. What the hell? Because he said Sartre. I mean, come on. All right, Kevin.
Yeah, I'd say functions are a form of data that are able to, what would that, transform or adorn regards to with another form of data. That could be another function, that could be another literal, or cause a side effect outside of the original scope. But a function is a piece of knowledge.
Okay. Yeah. So you have to include a philosopher in whatever answer you're giving. If you're honest. Yeah, go for it. Yeah, Jakob. Yeah. Nothing. Are you going to be that trivial about it? Okay. How many more? 2 more. Kevin.
So I'd say a function is a mapping from a set of functions into a new set of functions. And I would say data is the identity function.
We'll take that into consideration. Luke, you might need your help here.
So if you think about what you're doing as a graph, you could have your data be the nodes and your functions be the arcs, and how you get what nodes together.
Okay, 5. Ryan? Da-da-da-da.
Jonathan said it first, which is
So about because it has a philosophical bent compared to the nothing. There's no difference. Okay. Jonathan, you get a bottle. So thanks everyone. Thank you very, very much. I hope you learned something.